Great. Well, it's now noon in Moscow and in Sochi, and I'm glad to start the last talk of today's morning session. Sabir Gusein-Zade will tell us about Alexander polynomials of algebraic knots and links, Poincaré series, and their real analogues. So let's welcome.
Okay, thank you very much for inviting me to give a talk at the conference. Probably excuse me in advance for some husky voice because I have got some cold just recently. So I have some, I'm a little bit squeezing and so on. My talk is about some class of knots. These are algebraic knots, which are, I'll give in the definition in a moment. They are, of course, far from being very general knots, but it appears that their analytic invariants are similar to, are related or even coincide with topological invariants, and there are some real analogues which give hints to consideration of some knots in spheres with additional structures from my point of view. So let's start. An algebraic link in a three-sphere is an intersection of a complex plane curve. So one takes a complex plane curve, gem of a complex plane curve in the complex plane, and it intersects it with a small sphere, gem at the origin, of course, and intersects with a small sphere of radius, small enough radius, centered at the origin. So the number of components of the an algebraic link, which is in the intersection, coincides with the number of irreducible components of the curve gem. In particular, this link is a knot if and only if the curve is irreducible, consists of one branch. So all algebraic knots, for example, are iterated torus knots, but this is far from vice versa. Now, for example, one of trefoils is algebraic and the other one is not. Maybe this example is not so important in other sense when you have no, in any case, there are restrictions which distinguish algebraic knots in between torus knots, but this is, I don't want to try to formulate them. The Alexander polynomial of an algebraic knot has some special properties. For example, first of all, it is cyclotomic. In some sense, cyclotomic means that it is product ratio of binomials of this form. I mean, of course, cyclotomics usually sometimes is used for a little bit another, but cyclotomic in this case is, I mean, it is product ratio, finite product ratio of binomials of for the form 1 minus t in the power m. And moreover, all the coefficients of this series, if you divide the Alexander polynomial by 1 minus t, then you get a series with coefficients only 0 and 1. This is rather special property. And so now, what about, I'll discuss some initially analytic invariants of algebraic knots, or rather of plane curves corresponding to, or gems of plane curves corresponding to them, and they are related with the notion of valuation. So valuation of discrete of rank 1 on the ring of gems of holomorphic functions in two variables is a function on with values in non-negative set of non-negative integers and also plus infinity, with the following property. First of all, nu is the name of the valuation. Nu of lambda g is equal to nu of g for a non-zero lambda. Then nu of g1 plus g2 is greater or equal than minimum of nu of g1 and nu of g2. And finally, nu of the product g1, g2 is nu of g1 plus g2. So one remark, sometimes in the definition of evaluation, people write that people demand that each non-zero element in the ring has finite value. But in this definition, we permit to have a value equal to infinity for non-zero function gem. This sometimes people call semi-evaluation, but it doesn't really matter. If it is necessary to work with valuations, one can work instead of C20 instead of gems of holomorphic functions on the plane, one can work on in the ring of holomorphic functions on the curve itself. So for my talk, there will be no difference. The difference may appear only in some computations, which I skip, of course, and so there is no. But I will prefer to work in the plane. So each irreducible plane curve gem defines evaluation on the ring of functions in two variables, or gems of functions in two variables, which is called the curve evaluation. So essentially, there are mostly two main types of evaluations on the ring of functions of two variables, so-called curve evaluations and divisorial evaluations, which are not interesting in the context of this talk, and all others are very close to them. They are not important. So the curve evaluation is defined in the following way. Suppose let us take a parameterization of the curve. To your regret, at the moment I found that C, which is complex field, and C, which is a curve, are rather similar. C is upright, in an upright position for the complex plane, and a little bit italic for the curve. But it was somehow late to try. No, not to. Maybe I could do something. So it was late to try to change, and also, so excuse me, but I hope that it will be understandable. So we take a parameterization of the curve. It means that a map from C to C2, so that the image of the map is our curve, gem of our curve. This is a local map. And phi is an isomorphism between punctured neighborhoods of the origin in the complex line and the curve C. So phi is a local parameterization. Now, for example, curve can be parameterized like x is equal to t squared, y is equal to t cubed. This curve will give the trefoil, just the trefoil, one of two trefoils as the corresponding algebraic nodes. And so, and then if we take a function gem in two variables, g in OC20, then the value of this valuation, mu c, is defined as the degree of the leading term in the Taylor series decomposition of the function g of phi. So you apply to phi of t, you apply j, and you have function of tau. Tau is the parameter on the complex line on C, the complex line. And so if you decompose it into the Taylor series, you get the first term, A times tau in the power nu c of g. So the degree of this leading term is called nu c of g, just the value of our evaluation on g, no, plus terms of higher degree, where A is assumed not to be equal to 0. This is the first non-vanishing term in the Taylor series decomposition. Now, if by chance G, the composition of G and phi is identically 0, that is, if G is from the ideal of functions vanishing on the curve, then we simply define the value of nu c on G is to be plus infinity. This is just the set of which gives infinity. Okay. So then there is a notion of a Poincaré series. So if you have a collection of valuations in this sense, which is here, in particular, for example, a collection of curve valuations, then there is a notion of the Poincaré series. It is so if you have R valuations, you have Poincaré series depending on R variables, and it somehow Poincaré series is usually applied. The word Poincaré series is often applied to a filtration, and for one index filtration, that is R is equal to 1. The idea is so the Poincaré series is the one which people know very well. So if you have a one index filtration, so here J of V is a filtration. J of 0 contains, J of 0 is the total ring. J of it contains J of 1, it contains J of 2, and so on, decreasing filtration. Then you take the dimensions of quotients, of subsequent quotients, J of V factorized by J of V plus 1, and write down the generating series of this dimension. This is the usual definition of the Poincaré series for a one-index filtration. This is nothing, how to say it, surprising or strange or whatever, just a moment. So, but for so in the case of several valuations, in this case which I discuss, so you have R valuations. The Poincaré series is also related to a filtration on the ring of functions. So which filtration is used? So suppose you simply take R index filtration, which is defined in the following way. So here it is J of V, the equation 1. So you take J of V. V is the index, the multi-index, V1, etc., VR. No, I write here that it belongs to Z, to the positive positive octant, to the set of Z lattice in the positive Z greater or equal than 0 in the power R. But for the definition, strangely, I'll extend this definition a little bit to a bigger space, bigger lattice, bigger part of the lattice. So we simply take the set of functions, gems of functions, set that nu of G, nu underlined of G, is greater or equal than V. What does it mean? Here V is V1, etc., VR. As I told you, this is the index of our, which numbers the elements of the filtration. And nu of G is assumed to be simply nu1 of G and so on, nu R of G. The values of our valuations on the on G, on a function. And we assume that the ordering is the complete, the component wise. It means that it's not total order, it's partial order, of course. That say V prime, which is V1 prime, etc., VR prime is greater than V, which is V1, etc., V1, if each component of the first vector is greater or equal than the corresponding component of the second vector. Natural. I mean, this is ordering component, they are ordered component wise. Okay. But it is strange, but in order to give a definition, which I'll discuss in a moment, definition of the Poincaré series, one needs to extend this definition, which is written in equation 1, to all V in Z in the power R. That is to permit negative elements in negative components in V as well, or integer components, but nevertheless. The equation does not, of course, does not permits to do that, no problem, of course. So one considers multi-index filtration of a ring or of a vector space, it doesn't matter. And one wants to define the Poincaré series of this filtration. As I told you, when it is analog, it is an analog of, should be an analog of the Poincaré, of the usual Poincaré series of one index filtration, where for one index you simply take the dimension of the quotients of subsequent elements of the filtration and take the generating series of them. This is, I showed you this equation. This is just, you take here V is not underlined because V is you have one index filtration with simply a number, and so you take this. So for the multi-index filtration, the definition of the Poincaré series, which was first given, as I wrote here, was given by Campillo, Delgado, and Kirik. By the way, Campillo and Delgado are co-authors of the of my talk in some sense. I mean, of the subject which I discussed. It was given, and this definition is looks here. So you should take for this series. It is series which lies, I would say, not nowhere, but the set of this series is not a ring, is not a maybe model of polynomials, but not ring because you cannot multiply them, and so on. This is infinite, a series infinite in all directions. So you take for all v in the lattice, in the integer lattice, you take this codimensions. One underlined means 1, 1, 1, 1. So you take j of v1, etc., vr, and factorize by j of v1 plus 1, v2 plus 1, and so on, vr plus 1. And then you take these quotients, their dimensions, and you multiply by t in the power v. And take the generating series, take this in series with formal series in our variables. And then you write this this equation as a Poincaré series. I must say that I understand very well that the equation looks maybe not crazy, but very strange, maybe even crazy, because for me, it looked really strange when we first started to work on this subject. They told me, oh, we know what should be, first we made something for one curve, for a reducible curve, and then when we moved to curve with several branches, they told, oh, we know what should be considered as the Poincaré series. It is this one. I told them, excuse me, it is very strange, absolutely abnormal. Here is certain series in with negative, with indexed by with powers, no, like Laurent series in some sense, but Laurent series is usually bounded from below. This is not bounded from below, and there is another strange equation. I tried to convince them that one should give a sort of more natural, from my point of view, equation for the Poincaré series. But after some discussions, and when it was understood, when I understood that this definition nevertheless is related to some geometrical and topological object related with the filtration, I was found that this was, so from first point of view, the definition looks very strange. I understand this very well. This was my first impression when I saw it. Now, of course, I know that this is really a proper. In fact, this is something like that. This is written something like that. That one takes quotients in directions of the coordinate lines, take their dimensions, and then apply the inclusion exclusion formula to get the corresponding coefficient. Maybe the definition looks more convincing, but I don't want to have no time to make it. So as I told you, if you have r equal to 1, so there is one index filtration, then the Poincaré series is a very natural one. This is just this nothing series. For a curve valuation, the coefficients which are here, if you have one curve valuation, then the coefficients in this series are always 0 or 1. This is just because if you have two functions which are in j of v, it means that if you take there as functions on the parameter on the curve, then they are start from, and you look at, they start from ai t in the power of v. So the leading term is like that. Then this combination, of course, they are linear. This combination belongs to j of v plus 1, obviously, because the leading terms disappear. And this means that they are G1 and the G2 are linear dependent in the quotient. And so the dimension cannot be greater than 1. And so this series it has coefficients 1 or 0, and this means that the Poincaré series in this case can be written as simply sum of t in the power v, where v runs over all values, all integers which can be which are values of our filtration of our valuation on functions. So as C is by definition what happens here. Here I put square brackets instead of curly brackets. So here it's a misprint, of course. V belongs to z greater or equal than 0. Greater or equal than 0 is in the lower index, such that there exists a function gem with the value on it equal to v. So this is set of values which are taken by the evaluation, and this is of course a semigroup. This is called the semigroup of values of the evaluation. This is semigroup just because of this property, the property 3 of evaluation. So if you have two functions, two values are taken by the evaluation, then their sum is of course also taken by the evaluation. This is a semigroup with respect to addition. So by the way, there is the notion of the semigroup of values is of course works for multi-index filtration as well, but analog of the equation for the Poincaré series does not exist. This is the reconstruction of the Poincaré series from the semigroup is very involved, is very undirected for r greater than 1. So let us look. Now, an important result which made this subject somewhat exciting. So you see, up to now, I discussed some analytic invariance, some Poincaré series, analytic invariance related with curves. No, so with what I mean with curves. This here was I mentioned that I took gave a definition for any collection of valuations, but of course, from geometric point of view, I want to discuss valuations corresponding to an algebraic knot. That means that I take a curve gem, in principle, a reducible curve gem with several branches. So the intersection with a small sphere is a link with the same number of, and I take the collection of valuations defined by branches of this curve. And so we have R valuation, so curve valuations, but then we make some analytic computations and get some invariants, which from initially are analytic invariants of curves, and doesn't look, how to say it, related with traditional invariants of knots, in this case algebraic knots. However, there is the important result which was somehow made this subject somewhat exciting, was the following one, and which inspired somehow discussion, somehow development of this subject in some directions. No, I don't want so. There were some developments by Nemetzi for in the direction of invariance of three manifolds and so on. Nevertheless, the initial statement was the following one, that in fact this Poincaré series, which I defined in a strange way, really, as I told you, a strange equations, and if, from instance, from the first glance, a strange equation, which gives an analytic invariant, but nevertheless, it appears that this Poincaré series exactly coincides with the Alexander polynomial in several variables of the algebraic link, which is intersection of our curve with a small sphere, as I told you. So intersection gives a link with R variables, and if you take an Alexander polynomial, it is precisely the Poincaré series. No, in fact, it is the Poincaré series as it is written here for R greater than 1 when you have more than one branch. For I equal to 1, the relation is a little bit different, namely the Poincaré series is equal to the Alexander polynomial in one variable, of course, divided by 1 minus c. But this is not very important and probably even not very strange. By the way, this theorem, which is here, up to now, though it is a relatively old theorem, up to now, this equality between the Poincaré series and the Alexander polynomial has no conceptual explanation, though there were some people who tried to find it. I mean, there is no reason why this equation with evaluations and so on is really related to some homologies of the complement of the covering of the complement and so on, to topological invariance around it. So this equality, this was proved in the following way, and all the proofs which there were some other attempts, some other proofs, but they all looked like that. There were, roughly speaking, computations of the both sides of the equality of the Alexander polynomial and of the Poincaré series in similar terms, in one and the same terms. Now, for example, the initial one was in terms of a resolution of the curve C, of the embedded resolution, when you make several blow-ups to resolve the curve, you get a resolution, and in terms of resolution, you can compute both of them. The Alexander polynomial is a well-known equation which one can find, for example, for an algebraic note in the paper of Eisenbach, and in the small book of Eisenbach and Neumann about three-dimensional. No, I forgot the name of the book, a rather well-known book. But computation of the Poincaré series, which was independent of that one, led to the same answer. And this is the only way to prove this identity up to now. This is somewhat strange, but no, what does mean strange? It's the reality. By the way, this statement, also this statement about the Poincaré series, first of all, it implies that actually the Poincaré series, which initially, as I told you, was defined in completely analytic terms, is actually a topological invariant, even a complete topological invariant of an algebraic link, because it is known that the Alexander polynomial in several variables is a complete topological invariant of an algebraic link, not of course of any link, but of algebraic links. And this was relation with topological invariance of knots and something with algebras of functions was extended by Oblomkov, Shende, and Malik to the Homfliff polynomial. So it gives their result gives for Oblomkov and Shende gave a conjecture, found this and proved it in some simple classes, and Maulik give the complete proof for the Homfliff polynomial. And Homfliff polynomial is expressed in terms of the Hilbert scheme of zero-dimensional subschemes on the plane curve singularity, on the plane curve. By the way, roughly, Hilbert scheme simply means that this is the set of ideals, no finite codimension, I mean, except the zero ideal, non-trivial ideals in the ring of on the curve, of functions on the curve. And one can say that the Poincaré series, when we consider functions, we simply work with principal ideals. So this is part of course, as usual, Alexander polynomial is in some sense specialization of the Homfliff polynomial, and so the result of. Okay, so it's now in particular, I have a little bit delay, not a little bit. So it was shown the Poincaré series can be expressed in terms of an integral with respect to the Euler characteristic. This is an equation. So you can look at the productivization of the ring of functions and integrate this monomial. The Euler characteristic here must be the additive Euler characteristic because which is expressed in terms of the in order to have it to make sense to an integral with respect to the Euler characteristic as it is here. One can write a sort of a finite dimension analog of it, namely one can take these spaces, take up again, here is a mistake, okay, it doesn't matter, I'll maybe nobody will notice. So one can take these spaces, take j of v factorized by j of v plus 1. This is a finite dimensional space in our case, in the case of curve evaluations, and subtract all quotients when you take a deeper, so v plus 1i. I is a subset of I0, 1, etc. So this is the union is a natural, say, semigroup, which is called the extended semigroup of the collection. And the equation is that here is that it can be expressed as the genetic series of Euler characteristic of, here it is not written, it's a mistake, here must be P, productivization of V. You have characterized by action of the non-zero elements. Okay, now we move to the somehow an algebraic link usually is embedded into the three spheres. I understand which is in the complex plane, three sphere in the complex plane, and expressed in terms of the ring of gems of holomorphic functions on the plane. But one can consider the complex plane as a complexification of the real plane, which is inside it. And instead of looking at the complex functions, holomorphic functions, one can look at the ring of functions. No, let it be real analytic functions. It's not very important, but real analytic functions on the plane. So any evaluation on this, the set of real function is in fact the restriction of evaluation on OC to 0. This is a general statement. And in particular, any irreducible curve inside the complex plane, complex plane curve, of a complex plane curve, defines evaluation on the ring of real functions on R2. And so one can get look at the collection of evaluations here, and then of course you have a link. If you have a complex curve, you have a link in the three sphere. And you can define sort of Poincaré series and look at this complex curve. But you can look at the complex curve in the sphere with additional structure. What is this additional structure in some sense? Not in some sense. Additional structure on this three sphere. This three sphere carries essentially the additional structure is the following one. Let us look. There is a complex conjugation on it. So of course this three sphere in C2, consider the complexification of R2, has the involution of the complex conjugation with the fixed point this circle, the real circle, the intersection of R2 with this sphere. So in some sense, one can say that now we consider a link in the C sphere with this additional structure, algebraic link, but with this additional structure, with the conjugation, with the involution of conjugation. So then one can look at all these equations, which I discussed before, and in fact apply them to the real setting. What does it mean? So in this how to say, the Poincaré series which was defined, one has simply write down, instead of spaces filtration in the ring of gems of holomorphic functions, one has to write down the ring of gems of real analytic functions, take these quotients with the same quotients, and take the dimensions here, real dimensions, of course, because this space is in principle has no complex structure in principle, because sometimes there is complex structure, strangely. Then you can also integrate over, write down the equation which was written here, as I wrote you, is integral with respect to the Euler characteristic. I didn't tell that this is integral, of course, of over the infinite dimensional space, and to make a definition, how to say it, precise, one has to use sort of ideas which are used for Mativik integration. In some sense, this was inspired by that. But now you can again integrate over the projectivization of the ring of functions, real functions, and here is differences. I'll tell you about the difference in amount. Then you can write again these objects which are called extended semigroup, as I wrote here in this space, and take their Euler characteristic. Again, there is a misprint because, of course, it was copied from that. Here must be P in equation 9, Euler characteristic of the projectivization of these guys. You have to factorize by the action of the non-zero element, non-zero numbers. And finally, for one valuation, if you have one valuation, curve valuation, you can take simply the generating series of the values like that. But the set of values is different. If you consider functions which are real, then the valuations are not those. There are less elements which are given by that. So the main differences which are here work like that. First of all, now, for example, if you have one curve valuation in the complex situation, I explained you that any two curves, any two functions are in J of V, are linear dependent in the quotient by J of V plus 1. And so all the coefficients were 0 of 1. But if you have two gems, then in J of V by J of V plus 1, they can be linear independent over C. As usual, they are linear independent. However, they can be linear dependent. However, they can be linear independent over R, even if they are real. So this means that the coefficients in this series, in this series, in this one, can be now either 0 or 1 or 2, which is, in fact, in the latter case, this quotient has a natural structure of a complex line, though the definition is completely real. However, there is, and so this produces some big difference. And also the problem, especially for computations, to apply technique for computation of the Poincaré series elaborated by us, was the following one, that in the complex case, the affine line has Euler characteristic 1, I mean additive Euler characteristic. But the Euler characteristic of the real line is -1. Real line is nothing else but a cell of dimension 1. So this additive Euler characteristic is just the number of cells of dimension 0 minus number of cells of dimension 1 plus number of cells of dimension 2 minus etc. And so the real line is a cell of dimension 1, and because of that, its Euler characteristic is -1. Therefore, the Euler characteristic of a complex affine space is always equal to 1, whereas the Euler characteristic of the real affine space is sometimes 1, sometimes -1, and this makes quite a difference. So, in fact, the equation, this one, which was important for even for some computations later, the initial computations of the Poincaré series were in fact made by, roughly speaking, by equation 9, by reduction to equation 9. So Euler characteristic, and was worked very important. There were topological considerations, but in the space of functions. And In fact, this equation gives something which is almost equation 8, something which seems to be almost uncomputable. No one can write a very long equation for that, but the answer is very ugly, and one can. So it's better not to. Even for the case of one evaluation, the answer is not pleasant, roughly speaking. However, so the answer, but in other cases, there were, so this was for, in fact, as I told you, there are some complications, mostly related with the fact that the Euler characteristic is not always 1, but sometimes 1, sometimes -1. And this, so I must say that the computations usually apply the Fubini theorem. But Fubini theorem was applied because, roughly speaking, all the fibers had Euler characteristic 1, whatever this means. I don't want to discuss where the Fubini theorem was applied. But when the fibers have Euler characteristic sometimes 1, sometimes -1, it is very unpleasant and almost difficult. It's computable but general computations were not produced up to now. I means for general algebraic links. However, for algebraic knots, it means for one curve evaluation. If you have a curve with one branch, then the answer, then this all three other Poincaré series given by equations, as I told you, 7, 9, and 10. No, in fact, the answer for 8 was also given, but the answer, as I told you, was very ugly, so we skipped it. It's not interesting. It looks almost senseless. But the answer was given in terms of a real resolution of the curve C. What does mean real resolution of the curve C? It means that one has to make to resolve the curve C, but to use always blow-ups either at real points, or if one blow up a complex point, one has to blow up the complex conjugate one as well. So that the resolution should be real resolution. One needs to have the complex conjugation on the space of resolution as well. This is in fact simply means that one has to resolve the union of the curve with its conjugate. If you take the curve C and why it's again a misprint. When I give a talk, I see now that there were, so I tried to clean all misprints, but you see, it's of course not intersection here of C with C bar, but union of C and C bar. One has to take the curve, the union of these curves, C with this conjugate. The intersection is usually 1 point. It's not interesting. And so the answer is in terms of this resolution of the, roughly speaking, graph of this resolution, whatever this means. So I am not really sure. In fact, now it is absolutely clear. Initially I wanted to prove, even I put some hints about the answer at the end, but I see now that it was initially I didn't want to give precise answers, just because first of all, I need to, in order to give the precise answers, I need to introduce quite a number of data and so on. This is not interesting. No, not interesting. This probably is interesting, but I don't want to do. If one wants to see an answer, one can look into a preprint. The paper is at the moment in the preprint. It is also submitted to Bulletin of London Mathematical Society, and there was a affirmative report, but after the revision has to be evaluated again. So because of that, I don't want to write down the precise formulas. I'll simply it is, from my point of view, it is more interesting to describe some properties of these answers. So first of all, all three, as I told you in the former times, there was one particular property, in fact, which worked in all our computations, even in the multi index situation, that the Poincaré series was cyclotomic. It was a finite product or ratio of binomials of this form, y minus t in the power m. Now, for example, if you remember the Alexander polynomial of the trefoil is 1 minus t in the power 6 divided by 1 minus t squared, 1 minus t cube, which is just what is product ratio of these binomials. And this is a general statement, and also for usual knots, and also for these real versions which I described. All three of them are cyclotomic. They are products of binomials of this form. This is first property, which is interesting. The other one is the following one, that this Poincaré series, which is given by equation 10, which probably is a little bit reduced with respect to other one. But this Poincaré series, we called it semigroup Poincaré series, is in fact always equal to the usual Poincaré series of another plane curve gem. So we started with a plane curve gem C and computed C in C2, which is the complexification of R2. And we this Poincaré series, which is here, appeared to be also the usual Poincaré series without any consideration with the, so the usual, by the way, Alexander polynomial divided by 1 minus t in this case, of another curve C prime, which is no, for example, if the curve C of our dog is, for example, if the curve C was given by the parametrization, just a moment. Ира, Ир, успокой собаку. Ира, Ир. Excuse me, please. So if we take the curve, which is given by the parameterization, x is equal to the power t to the power 4, y is equal to alpha t in the power 4 plus t in the power 6 plus t in the power 7, with alpha, where alpha is a generic complex number. No, in some cases, when alpha is -1, it is the same. It doesn't matter. Then the curve C prime can be taken like that. X is equal to t in the power 4 and y is equal to t in the power 10 plus t in the power 11. For if C is given by, it's similar, as the complex curve, it is topologically the same. But in the real setting, it is completely different. And when you look at the involution, if it is like that, x is equal to t in the power 4 and y is equal to alpha t in the power 6 plus t in the power 7, where alpha is a generic complex number, then the corresponding curve C prime is can be taken this one, x is equal to t in the power 4, y is equal to t in the power 6 plus t in the power 90. So in some sense, to each curve in the complex, in the this real setting, in this sphere with this additional structure, with this involution, one associates another curve, at least topologically, in the sphere without this additional structure. And now, yeah. And now, also, as I told you at a moment, the Poincaré series of and so Alexander polynomial in several variables is a complete topological invariant of the curve. And so since Poincaré series is just this coincides with it, it is the same. But here it is a little bit different, not too much, in fact. As I told you, there are three versions of the Poincaré series, and one of them is discussed here when we have a series with only 1 and 0 as coefficients, and then it gives us another curve. But this series is somehow, I told you that it is a sort of degenerate version. I don't want to discuss why it should be considered as a degenerate version of the other two. But this one does not determine even the topology of the curve C. When you may have, by the way, in some sense, this is just the reason why here we have identical curves from topological point of view. C here was this one T4 alpha T4 plus T6 plus T7, and also T4 and alpha T6 plus T7 from topological point of view are the same, but the Poincaré series are different, and because of that, somehow this doesn't determine the topology of the curve C. And so this means that it doesn't determine the topology of the pair C squared and C, so embedded topology of the curve C. And so, and therefore does not determine its real topologies. That means the topology of the curve C, again, here is a misprint because I simply copied it from another place. It is, of course, union, C union C bar. And here is C union C bar. Excuse me, please, for misprints. The topology of this curve. However, the other two series, the other two versions which were there, which I mentioned as the computations, they both of them determine the topology of the curve C union C bar. It means the real topology of the curve C union, not intersection, and therefore in particular it determines the topology of the curve C. This is very so. Hopefully, there must be generalizations of these statements for more variables, more curves with more branches for links, but at the moment this is not elaborated yet. Okay, so I tried to be precise, and excuse me for being a little bit slow at the beginning and then to try to rush because I wanted to finish at the assumed time, and I almost succeeded. Thank you very much for your attention, and this is the end.
Okay, thank you very much for your talk. Well, I had a very small question. Though the Alexander polynomial may be complete for algebraic knots, are there any attempts to construct Higger-Floer homology for algebraic knots?
Excuse me?
So though Alexander may be complete for algebraic knots, were there any attempts to construct the Higger-Floer homology for algebraic knots?
No, we didn't try this, and but I must say that somehow no, we didn't do that. I don't want to no.
It does sound like there might be a conceptual explanation at the level of categorification.
Of course.
If your Poincaré series, your algebraic Poincaré series, had a categorification that could be compared with Heegard-Floer, yeah.
Of course. Moreover, when we made that, just at the same moment, there was the categorification given by Khovanov homologies. And just at that moment, we wrote that our construction, in fact, gives a sort of categorization of the Alexander polynomial for algebraic knots. Moreover, in some sense, our construct, and I wrote a letter to Khovanov at that moment.
But does it? Because you know that the Heegard-Floer is a categorification for the Alexander polynomial.
No, of course. Yeah, you are right. But I mean that there was made something for algebraic knots. There was even in our construction there was even more. It was not only, we didn't only constructed complexes which Euler characteristic, whose Euler characteristic was that, but we constructed spaces. For algebraic knots, these are spaces. This was FV I wrote there. You maybe remember.
Do you have papers on that?
In some sense, for algebraic notes, we presented spaces which gave us the.
Yeah. Do you have papers about that?
No, in papers there was no. It was how to say it. It was byproduct. Byproduct, in fact, not byproduct.
But
in the computations
you don't have a publication or an archive.
No, what do you mean? We had the initial paper where we proved that it is the coefficients of the Poincaré series are all characteristic of this so-called fibers of the extended semigroup. This was just the method which was used for computation of the Poincaré series in our initial publication in the Duke Mathematical Journal.
I see.
And we wrote somehow and then it appeared that the answer is the Alexander polynomial. So I told you that we gave it, but in a strange way, that it worked for the Poincaré series, but the answer was the same, appeared to be the same. Poincaré series appeared to coincide with the Alexander polynomial, surprisingly, or what mystery. It's as I told you, this is a sort of a mystery, but nevertheless, this is the case.
Thank you. Very interesting.
Well, the chairman disappeared.
Microphone. Yeah, any further questions or comments? Well, if it's not the case, so let's thank the speaker again.
Thank you very much.